videos. He's a very good modeler. And it just so happened that I thought I would pick up that case study. So his talk was a good segue into some of the work. What I'm going to talk about is something that will give you a feel for, like I said, some of the practical applications. And I'm going to talk about conjunctive use, which is where surface water, groundwater are combined. And I've chosen a case study or an example which will, utilize some of the material that we have sort of been going over. We did not spend a whole lot of time on actual modeling techniques. We simply ran out of time. But we are going to use in some of the modeling techniques therefore. I wanted to start with water resources management. Almost at any scale, continues to be a challenge. And especially if the problem that we are looking at is complex and involves a lot of factors, increase in water demand, increase in populations, and so on, basically do put a lot of stress on our water resources, whether they are domestic, agriculture, or industrial use. And one of the challenges that I find, not just in India, but in almost all parts of the world, is that we have not been able to establish very good regulations how to use water. The use is very much unregulated. We are obviously not happy if somebody is going to charge us, let's say, for our use of water. And in fact, I don't know how it works in other places, but my parents used to live in Visakhapatnam, and there they paid one flat water tax. Water was not metered. Electricity was metered, and you pay based on how much electricity usage you had, but water was flat. Once a year you would pay a certain amount of tax, and then essentially water was not being charged anymore, but we'd have to struggle with how often or how well the municipality could supply its water. And consumer behavior very much depends on what we are regulating. This is how we behave as human beings. Because power is regulated, we tend to be more careful about how much power we use. We look at the electricity bill, and therefore we make decisions about how we use power. Water, regrettably, is not regulated in the same fashion. When we talk about domestic and agricultural and industrial uses, those of course continue to be challenges. Climatic and hydrologic uncertainties, I think this is something that we all deal with. Whatever management practices that we want to put in place, we'll put them in place today, but we expect those practices to serve us for some future time horizon. They should be serving us for 20 years, 40 years, 50 years into the future, not just for today. But will all the factors, all the driving forces remain the same for the next 40, 50 years? No, obviously not, especially when you put it in the context of climate change, which basically suggests that what we have seen in the past may not be replicated in the future. It makes it a big challenge. And that's a challenge that we face. Same with, how do we assess because of environmental impacts and changes that are going to occur in land use and practices. These cannot be predicted very well. Therefore, they continue to be a challenge. And another challenge that I see is in most of these studies, in practical applications, there is what I would call a lack of data, certainly a lack of good data, lack of enough data. We might have very good and complex models, but these models require a lot of data for them to be used at their full potential. That may not be available, okay? And all of these basically plague issues with water quantity and quality. And these challenges, as I said, they are not specific to a particular location. I see them all over the world, okay? To address some of these challenges, hydrologic modeling is a tool that we employ. So some of the basic things that we have learned, they are essentially converted into computer models using differencing techniques, finite elements, finite differences, finite volume, what have you. We use this mathematical framework for describing even large hydrologic systems. So some of the problems that the previous speaker, Anupama, when she was talking about, or when Professor Shekhar was talking about, these are fairly large systems, not one single well, for instance. And our best tools, I believe, are still good mathematical models. Okay. They're useful to study, identify, and evaluate possible solutions to management problems. And I'll try and give you a flair for what that looks like in this particular application. As I said, computer simulation models, I still believe, are very useful in that regard. Okay. There are some things that models can do, some things that they cannot. And the fact that we have now more and more powerful computers and more powerful techniques also suggests that there are more things that we can do, perhaps better than what we could do just even 10 years ago. Okay. This is the picture of the basin that I'm going to talk about. So I'll try to give you some feel for what the problem is. So this is the Rattlesnake Creek Basin. It's essentially a part of south central Kansas. Kansas is right in the middle of US. It's the heart of the, it's perhaps the center of the, it's a centroid for US. And within that state, you can see some of the various counties, but this is the Rattlesnake Creek. The name, it gets that name because the nature of this, or the way the stream looks. And what you see is the boundary of this watershed. Okay. The Rattlesnake Creek Basin, as we say, it has been an issue of controversy for a long time, continues to be. The study that I'm going to present is a little dated. It was conducted in the late 1990s. But what we developed for this particular basin is still being used today to manage water. And so we'll try and give you a flair for that. So what essentially you are saying, this is the Rattlesnake Creek, essentially going to be flowing in this northeast direction. And so this is the downstream end. What is very crucial is that towards the downstream end, if you can read it, it's the Quivira National Wildlife Refuge. It's actually a natural wetland. It's a very important natural wetland. And then downstream of that, the Rattlesnake Creek continues, but there is quite a bit of modification because of this wetland. And along the way, you have various places where you have stream gauging stations, you have water monitoring wells, and so on. But this is basically what the watershed looks like. It's this long, elongated watershed, okay, the Rattlesnake Creek Basin. The Rattlesnake Creek Basin basically sits on what is called as the Ogallala Aquifer, which you might have heard. So in the central part of the US, it's a large aquifer which supplies water to Kansas and neighboring states, but like many other aquifers, does suffer from overexploitation. Okay, so there's a lot of context to this problem. Okay, so just to give you some more details about the basin itself, it's, like I said, a long, elongated basin. 62% of the basin area is non-contributing to stream flow. So what that means is the topography is such that there are many local depressions where if the waterfall it fills up, that water doesn't actually flow and topographically reach the stream. It just sits there as a non-contributing area, okay, which becomes important when you're trying to do surface water management. Based on classifications and so on, we have 4 land uses and 5 dominant soils present, and those represent the basin conditions, okay, fairly well. So data that we have for this watershed, which is going to be very important, is we have an idea of the land use and the soils in that basin. We have measured weather. We have stream flow data at some locations. We have something called reported water use. So this basin is also heavily agricultural dominated. Many farmers, they all have wells, just like the problem that Professor Shekhar was talking about today. And the farmers are not charged for their water. They are asked, they're requested, if you will, to report how much water they're using, but that's also voluntary. They don't have to report it. So those who choose to report it, we have that information. So I said reported water use. And of course, whenever we study a basin, we essentially walk the basin as it's called, but basically we drove in the basin and got a feel for what it looked like and so on. Okay. So so within Kansas, which is in the center of US, this is the entire state, the Rattlesnake Creek Basin is right over here. And what I'm showing in this map is in the Rattlesnake Creek Basin, and some pieces of information where we have climatic stations. The important things that we'll have are the stream gauging stations. And let me see if I can, there's one at Maxwell over here, okay? There is another one at Zenith over here. There is a gauging station at Raymond, but we are not directly able to use it because the flows at Raymond are very heavily influenced by what happens in that National Wildlife Refuge. So that's not unrestricted flow. So it cannot be modeled unless we are able to model what kind of flow diversion practices exist. These contour lines sort of show what is called as pre-development water table contours. So before all these farmers were given permission to extract water, so over that basin we have information on, based on all the wells that they had, we have some idea of what the contour lines for the water table heights. Okay, and then we have several observation wells, and you will see OW1, OW2, OW3, OW4, and so on. So these are observation wells where we have some record of water levels. Then there are some index wells as well. There are some irrigation wells, but the observation wells essentially also provide us with information on groundwater elevations. So this is the kind of information that we have as we basically start to study the watershed, study the aquifer, if you will. The problem that was being faced, let me see if I'll come to it. Okay, here are some pictures of the Rattlesnake Basin. This is part of the stream, the Kuvera National Wildlife Refuge. I should say something about the wildlife refuge. This is actually a very large natural wetland, and it's a very important wetland because it's in the path of migratory birds, which fly from South America all the way to North America and past Canada. And these birds, as they're flying, they have genetically coded, I suppose, particular stops where they will rest, drink water, and then move on. This happens to be one of those flight paths, so one of those stops for them. So it's extremely important, to preserve that. If the birds come and let's say this wetland is dry, it's not like they look around for some other water source. They just continue on. And what happens then is, of course, they have not been replenished, so they don't make the journey, they die. But they will not look for another source of water. It reminds me of a poem by Shiv Mangal Singh Suman. How many of, well, perhaps you guys are way too young for this. He wrote a poem called Hum Panchi Unmukt Gagan Ke. It's a very nice poem. If you get a chance, you should read it. But when I was studying this watershed and learning about the ecology of these birds and so on, I was reminded of this poem because that poem, there are a couple of lines which says, this is basically about freedom fighting and all that stuff. That's the background. So there's a line which says, Ya to kshitij milan ban jata, ya tanti saason ki dori, which means either they reach the horizon, their goal, or they'll die, which is essentially what these birds do. And I suspect some of you, or at least many of you, might be familiar with this particular device. It's called a central pivot. And this is what is used for irrigating water. So the fields are fairly large. And what you have is a very long pipeline that you can see. And at the source, there is a well. The water is being drawn from the well, comes through this pipeline, and then irrigates the field. And at the well, it's anchored, and then this wide arm goes in circles. So when they plant the crops so that the wheels, they have fixed path, and then they plant the crops according to that. And it's a fairly efficient way of irrigation because it does mist irrigation and so on. So minimizes losses. But they draw huge amounts of water. So irrigation use tends to be very, very high. And this is essentially one of those pictures that they have, which shows you that some parts of the surface are wet, others are dry. I talked about non-contributing areas. And this picture also gives you an idea of the nature of spatial variability that actually exists, where part of the surface are ponded, parts are not. And that's almost a separate research problem in itself. Okay. So let me talk about some of the issues in the Rattlesnake Creek Basin that motivated this study. The declining stream flows at gauging stations, compounded with declining groundwater level depletion in observation wells. So declining stream flows, as I said, is a big problem because if there is not enough flow coming to the wetland, then it's a big environmental concern. And of course, the groundwater keeps going down. That is also a concern. We talked about safe and sustainable yield right in the beginning of the workshop. Consequently, we have saltwater intrusion. And we sort of heard about this, in fact, in the talk right before this one. Kansas is right in the middle of the country. There's no ocean or sea anywhere nearby. Here, the saltwater intrusion is the main aquifer is the top unconfined aquifer. There is a semi-pervious layer. The bottom is a confined aquifer which has very brackish water. And if you overpump, remember there's a leakage thing. As long as the leakage is going from the confined aquifer into the main aquifer, it's fine. But if pressures change and leakage type gets reversed, then the water in this confined, this brackish aquifer enters the main aquifer. And as she was talking, if you do too much pumping, you're going to lower the piezometric heads. You change the direction of leakage, then you have a serious problem. It's very difficult to clean that up. So this was also beginning to be an issue. Kansas Department of Agriculture, in fact, the Department of Water Resources, therefore wanted to do this because the Department of Water Resources in each state is responsible for managing the water. So any design, everything, this is the agency that approves them. So what they wanted was a tool, a method that would allow them to manage water in this basin. There are several thousands of wells in that basin. And so they wanted to basically do what? They wanted to do a computer simulation model, which could do both surface and groundwater flows. Surface flows because we have the Rattlesnake Creek. We are essentially interested in what is happening to stream flows, and groundwater because we wanted to have each and every well represented in the model and basically be able to manage water resources. And basically the farmers, the state, they all agreed that they wanted a combination of a SWOT model, which I suspect many of you are aware of. So this is a surface water model. It's essentially a tool, does surface water, whereas ModFlow is our standard groundwater model. So ModFlow basically uses the governing equations for unconfined aquifers, let's say, that we talked about. But it uses it in Cartesian coordinates, and then wells are represented in those Cartesian coordinates as well. Both of these models are well documented. They have been seen quite a fair amount of use. And they wanted us to link these two models because SWOT model doesn't have a groundwater model. It doesn't even have an unsaturated flow model. Whatever water infiltrates into the ground, it basically leaves it off as deep percolation and then forgets about it. Whereas ModFlow does only groundwater flow, has no surface water component to speak of. So what you're imagining now is we have SWOT model on the basin sitting on top of ModFlow, and both of them have to talk to each other. So even as a modeling exercise, this was not what you would call a routine model where I take a model off the shelf and just run it. So SWOT mod, which is this combination model, needed to be capable of simulating both major components of surface and groundwater share. And once you do this, there are other challenges. We will not go through all of them, but one major challenge we'll immediately realize is we'll be dealing with disparate space and time scales. And I'll try and explain what that means. So groundwater flow, when we talk about groundwater flow, the water movement is fairly slow. Things don't happen on an hourly basis or a daily basis. In this case, ModFlow is being run at a monthly time scale. Surface water, on the other hand, moves very fast. The response time for surface waters are much fast. The SWOT model, in this case, runs on a daily time step. And so there are two disparate scales. So what you're essentially looking at is SWOT running over 1 month, 30 days. We collect all the 30 days values, see how much deep percolation on average is provided. That is then sent to ModFlow, which then uses this average as recharge that it's getting from SWOT over a 1 month period, does its calculations, but all the pumping that the farmers are doing, that ModFlow is doing. So whatever changes are there, however that affects pumping, this is then sent back to SWOT, and that is spread over the entire month for SWOT to use. So there's both space and time scales. SWOT basically does sub-watershed division. You'll see that, whereas ModFlow does a grid. So I'll briefly talk about the space and time scales. But this is trying to tell you a little about how we combine SWOT and mod flow and where all that information has to be exchanging for it to work properly and do a proper mass balance. It is complicated, it looks very complicated because there are many buckets where we are trying to manage the water. But most importantly, this is SWOT sitting on the surface. This is mod flow, okay? And SWOT basically receives the precipitation, does evapotranspiration, the irrigation water, which basically comes out of mod flow due to pumping, is coming back as surface water onto SWOT, okay? And there are you see many other components. There is surface runoff, which goes into the stream module of mod flow, and then mod flow does the groundwater. But lots of processes which then have to talk to each other for these two models to act together. Okay. So we did all of this. We built this model. So the modeling, basically, the surface water part of SWOT was the basin was divided into 35 sub-watersheds because SWOT works based on sub-watersheds and what it calls as hydrologic response units. Okay, it's a different way of doing things. Ponds option within SWOT was used to represent the non-contributing areas. Heterogeneity is done by weighted averages, sensitivity analysis for important variables. So these are standard modeling techniques that we do. What I'm showing in this figure is the spatial discretization of SWOT. So it has 35 sub-watersheds. So each of these is one sub-watershed all the way to 35. So this is the surface water. Underneath it is the mod flow grid, which is like a large rectangular grid, and that had about 50 kilometer by 50 kilometer grid size. And even then, we had something like 25 or 30 grid cells in this direction, and maybe about 200 grid cells in the other direction. And so the spatial discretization is all the cells that, let's say, lie within sub-watershed 2 in mod flow connect to this particular sub-watershed. All the cells that similarly lie below sub-watershed 4 on the mod flow grid connect to the surface water flow. So there's a lot of matching that you have to do both in space and time. But that's the modeling part. It also shows you the boundary conditions that we needed for the surface and for the groundwater flow. Based on what we know of the geology and so on, we have specified flux boundaries, we have no flow boundaries at some location, we have specified head boundaries at some location. Again, no flow boundaries and some other location at the boundaries of the watershed. So a lot of geologic studies and data were used to get at that information. Okay. So this figure shows you, the boundaries that were used to try and contain this entire watershed. When we do these kinds of exercises, we have no hope of knowing all the parameters. If mod flow has 2,500 or however many grid cells, we have no hope of finding the conductivity and transmissivity or sterility of each of those cells. We have to simplify the problem someplace. Similarly, for all the surface water components, all data that we need, they're not always available. So we go through this exercise of calibration and validation. The calibration and validation essentially says all these parameters that the model needs, we will try to estimate them by trying to find out what parameter values are going to make the model results compare very well with observations. And so typically what we'll do in the calibration phase is the data that we have is split up into two parts. The first part is being used for calibration. So this is the data that the model sees and basically fine-tunes its parameters so that the fit is very good. And then we take this best parameter set and see how well it does on the data that the model has not seen during calibration. That is validation. And if it's doing well in validation, then we have at least some corroboration that we think the model is reasonably good. At least it's reproducing what we are observing, with a reasonable accuracy. So we did the same thing. We went through the complex process of calibration and validation. The important thing is the data from 1955 to 1980 was used for calibration, and this was done over 20 years ago. Our validation period was 1981 to 1994. And when we do model calibration, a model like mod flow, which has many grid cells, we usually don't try to find different parameters for each grid cell. Based on the geology, based on what we know, we basically divide the whole area into areas that we think are homogeneous. And so that if I assign a value of K for 17.3, it's going to be applicable to an entire area. A K of 46 to 101 would be able to be applied to entire areas. So we do some zonation kind of thing, and for each zone, we'll find the parameters during calibration. Similarly, our estimate of recharge. Okay. And so the recharge also is estimated during calibration, but not for each cell individually. Again, based on the zonation, we'll have one recharge value for a fairly large region. And then, after we have done all this, we have estimated, then we do the calibration and validation part. And I think I showed you 1955 to 1980 is the calibration period. After 1980 is the validation period. We had stream flow. So what are our targets? We want to be able to match the observed stream flows, this combined model. We want to be able to match observed water levels in the wells. We would like to be able to match what the farmers report as their water use. So these are our calibration targets. And this begins to tell you what it looks like. So pre-1980 was the data that was used for calibration. And then the rest of the data is what you see is as a validation thing then. Okay, you have the observations, the observed values, and then the model predicted values. And typically we say this is about the level of performance that we can expect for calibration and validation. Similarly, if I look at observation wells, remember we had 4 observation wells. Okay. And in this case, there is a calibration period, there's a validation period, and then we projected way out into the future because we want to know if things continue as they are, then according to the model, what is going to be happening in the future. And so to do that, we have to basically say what is going to be the future weather like, what's going to be the future rainfall like. So in this case, in this particular case, our basic scenario is whatever the weather and everything was for the past 40 years, if that's repeated for the next 40 years, we will see how the model responds. And that basically, what this suggests is after calibration and validation, if we are to trust the model, the water level in the wells are going to continue to drastically fall. So this suggests that some sort of remedial action has to be taken. Otherwise, we are going to be depleting the aquifer. And this is in fact the state of many aquifers in the world right now. But this is our estimate of what would happen. So, and then when we look at these pictures, you see, well, in the area where we had data at that time, the model is at least showing the right trends. But it's a fairly serious picture. I mean, you have to look at the scale also. We are going from, let's say, 680 meters over here, 670 meters. 10 meters of lowering of groundwater is not something to sneeze at. It's a fairly, because we're talking about huge volumes of water in that 10 meters over the entire watershed. So these are the kinds of results then that we look at. And then, as I indicated, we have the reported water use by the farmers, and you can see what the model simulates. And usually this kind of data is required for us to have any confidence that our model is going to try and replicate somewhat reasonably what is happening in the field. And after we have done this, let's say we have this calibrated and validated model, and let's assume that all the stakeholders, in this case, the farmers, the State Department officials, the Quivira Wildlife Refuge people, the environmentalists, they all say, okay, we think that this model is doing reasonably well. And then they give permission to the state to then use this model for making decisions. And before the state makes any decisions, or what kind of decisions does the state make, it can see that the water levels are going to decline if nothing is done. So what then they do is something called a scenario analysis, which you're also quite familiar with. I think that is what these models are good for, is to evaluate different scenarios. So the first scenario, for instance, is reduce water use by 20% for the entire 40-year simulation period into the future. So we'll ask all farmers that 20% of your water is not going to supply, or you have to reduce your water use for irrigation by 20%. The other way to do it is reduce all water rights junior to file number by a certain amount. So these water rights that are given to farmers, and same thing happens in India also, depending on when a farmer applies for a permit to put a well and when it's granted, that is the date that they have the well. If I had a well which was given to me in 1980 and you have a well that was given to you in 1970, your well has priority because it was done earlier. So earlier, whoever got their permissions earlier, they have priority. So my water right is junior to yours because your water right was granted to you earlier. So if any curtailment has to be done, it's first done for the junior water rights. Then, and then it can progress to, and I think it's similar for India also. So another management scenario that they could try was, well, reduce all water rights junior to a certain water right by this much. Or turn off all wells within a 2.4 kilometer corridor along the creek and its tributaries. So if stream water levels are being affected, they are being affected because we're drawing water from the wells, and stream is hydraulically connected to the aquifer. So the stream loses water to the aquifer. And therefore, wells that are close to the stream, when they pump, water levels are more severely affected in the stream. So one management strategy could be within a certain distance from the stream, we will either stop or reduce pumping. But that's a scenario that they want to explore. So turn off all wells within a 2.4 kilometer corridor along the Rattlesnake Creek and its tributaries, reduce water use by 30% in a second corridor lying in a band from 1.2 to 2.4 kilometers, and so on. So these are the kinds of scenarios that they want this model to be able to do. Or scenario number 4, move all water rights from subbasins 16, 17, and 19 to subbasins 2, 3, and 4 evenly distributed. So 16, 17, and 19 are different subbasins. But basically, if we can, if drawing water at a particular location is going to cause very serious consequences, can the same water be got from somewhere else with less consequences? So, I think models are far better or far more useful for this kind of analysis. The water, obviously, this model is not going to predict what the water level is in the well 40 years from now. It will do prediction, but if we do not expect those water levels to match, that no model will be able to do that. But this kind of scenario analysis, asking what if questions, are very useful because then the state water officials can run these scenarios and see which scenarios are meeting their needs and perhaps cause the least stress to farmers, for an example. So scenario analysis then gives you these kinds of results. So what you see is the solid line is the baseline scenario. Okay, you have several results over here. This is index well 1, index well 2, index well 3. So 1, 2, 3, and so on. In each case, the solid line is the baseline scenario. That is the same in all of them. The dots that you see are the model predictions when scenario 1 is used. Under scenario 2, this is what is happening. Under scenario 3, this is what is happening in the 3 wells. Scenario 4, basically, this is what is happening at the wells. What are you trying to see then? How much recovery am I getting under this scenario compared to the baseline scenario if nothing were to be done? So that gain is what we are seeing as an advantage if that scenario is implemented. Each scenario also comes with a cost. You'll upset a lot of people. You'll upset a lot of the farmers because we're restricting their water use. But this is a kind of benefit that, and then whoever is making decisions, they look at these kinds of results and say, okay, which scenario or what should I be adopting? Obviously, if I'm looking at IW1, scenario number 4 did nothing to it. Scenario number 4 was going to move water rights from one location to the other, but index well 1 is not being affected by that move at all. So, whereas some of, if I were to basically look at index well 2, that scenario has a huge effect. Big difference. So this kind of scenario analysis is what our modeling studies are, I think, capable of doing, and do it well, because now we can make decisions. And our decisions are made based on physics and what we know. Similarly, the scenario analysis obviously also extends to the streams also. Under these scenarios, we would like to see, we have two gauging stations, Maxwell and Zenith over here. So this is for Zenith, this is for the various scenarios. And you can see that for the baseline scenario, for the baseline, do nothing, just next 40 years, the same climate repeats, we are not doing anything. This is how the cumulative stream flow is going to go up. But if you do implement the scenario, what is the gain that you are seeing in time over stream flows? So how much are the stream flow recovering? What benefits are we seeing? So this is also useful information. Now, this model, when it was done, it became a very highly complicated model. Required a PhD student and a half to run it now. Required a huge computer. So obviously, the people who are working in the state who have to make decisions, they don't have the time like a PhD student to basically just do this all the time. So they needed a decision support system, which basically says you put a front end on this model and a good back end so that these management scenarios can be very easily entered in. The model does all the running, and maybe a couple of hours or a day later, they come back and see the results to see what the consequences. So this is also more of a decision-making tool. We are not adding to the physics and to our knowledge, but we make this model much more useful for practical purposes. Okay. So DSS is a decision support system. So it's a friendly environment that allows us to enter what we need is the water rights and land use needed to be modified explicitly and see what the simulation results were doing. So it's again useful for a comparative analysis and long-term scenarios. So this is the decision tool, okay? This is the main stem of the Rattlesnake Creek Basin. It doesn't extend all the way over here because this is the portion that has water all the time. The upstream portions are ephemeral. Sometimes they have water, sometimes they don't. I'm not sure how clearly you can see this, but each of these green dots, you see those green dots?
Yeah.
So each of these green dots is a single well. And each of them is represented with their well number and so on, the decision support system. And therefore, when we look at a scenario which says some 1.2 kilometers from the stream, shut off all the wells, so all those wells that are in that stream, close to the stream can be shut off. Each of the wells has a number, it has a date when that right was granted. So if I want to say that all the junior rights are terminated, that scenario can be run through the system. But this is the level of detail that that was required to manage surface and groundwater in this particular watershed. And basically, this is just one of the screens. It says, select all water rights, change them by a certain percentage or a certain factor by a certain amount, run the analysis. What you can see, you are basically seeing the water right location, the number, the current water plan, what it is, proposed water plan, if you were to change something, how far is it from the stream, all this is now available to the decision maker. They don't have to be PhDs now in groundwater. And when they run it, they essentially get these kinds of maps, which essentially show the difference between the baseline, do nothing, versus what this management strategy does. So what is the change going to be between these two? And they say, okay, this is the impact. These portions are going to be impacted more heavily. This is where the wildlife, the quiver refuge is. This is how that's going to be impacted. So useful for decision making. Also, basically what the stream flow hydrograph is going to be at the zenith gauging station under this management scenario or in the baseline scenario. Same, it will also tell you if there's a baseline scenario which is red, under this management scenario, what kind of recovery are you seeing in this case, the groundwater levels in a particular well. So basically, they're the kinds of things that a model is able to do. And I wanted to give you some practical example of the kinds of things that we have talked about, or the kind of equation. We didn't talk about how to numerically solve them, which is what these codes do. But this gives you an example of how this kind of things are actually able to be used in practice and make. So this has been being used for, let's say, last 20-25 years. Every year, the decisions, if you have to imagine, on water rights run into the hundreds of millions of dollars. So very consequential decisions. But are based on some of these kinds of models that we actually build and work with. Okay, I'm going to conclude because I wanted to have some time for any questions you might have. So comprehensive integrated basin scale model, when this was done, this was fairly new. Now there are some other models. Many others have also used the SWOT model in their applications. I'm going to say model simulation results agreed well, whatever well means, in terms of how they represented trends. A user-friendly graphical interface was required for this model to be actually applied in the field because the model was way too complex. And this is, you have to imagine, 20 years ago, our computational capabilities have increased a lot since then. But so test management scenarios show that the present conditions could be improved by modifying water rights, and then we give it away to the decision makers. They have to make decisions. They basically evaluate these scenarios, but at least they are doing this evaluation, not by picking something out of thin air, but by using something that replicates the system reasonably well. So the decisions are more informed decisions. And then they are far more easy to convince stakeholders, look, this is not me doing it, this is our best understanding. So let me stop over here and see if you have any questions that I might be able to answer. Any questions? Integrated modeling and computer based that is contributed to a stream. Workflow does have a stream module, yes. But how does SWOT is computing the stream flows? Because SWOT can simulate the surface of models. Yes. But how does the SWOT is computing the base flow to the stream? So SWOT, I don't know how familiar you are with SWOT. I'm not an expert on SWOT. SWOT does both upland flow and stream flow. It does both of them. The stream flow is a combination of direct surface number. Oh, yeah. Base flow. So that's right. So whatever losses are occurring or whatever gains are occurring, that mod flow is providing back to it. If it's so, depending on how high the water table comes, it's a matter of whether it will contribute to the stream or. No. Only SWOT, yeah. I mean, only SWOT is nothing but surface. Yeah. Yeah. But SWOT will complete the amount of the stream flow. Yes. But stream flow is a combination of the surface and base flow. Yeah, yeah. So SWOT will. So SWOT is a model. It will only do what it is able to do. So SWOT basically has a mechanism where it says this much loss is going to be lost because of seepage or infiltration, either on upland areas or in the streams. That is all it's going to be able to do. It doesn't do anything with the aquifer in the contact with the stream. It's not meant to do that. So basically, you're saying it assumes that the water table in the aquifer is far lower than the stream, so that there is no hydraulic contact. SWOT will, any model, in fact, not just SWOT, any model will only do what it is capable of. So SWOT is not capable of figuring out what the base flow is. Not by itself. You might have to have another base flow algorithm which will tell you what the base flow in the stream is. So based on just observing stream flows and analyzing stream flows and using empirical methods, we are able to separate out what base flow is. So, but that is true. Yes.
So this you talked about this the time steps taken for mod flow, and because we run in. So basically, if you do it the same because for surface SWOT you go by day.
Yeah.
And if so you do it for 1 month, then you are lumping that into the mod flow, or
right.
how do you?
It is being lumped. So what happens is mod flow, because it's subsurface movement on a daily basis, you're going to incur a lot of computational effort, but hardly any change. So what is happening is SWOT runs for 30 days, accumulates all the results for deep percolation for that 30 days, averages it out, and provides it as a rate to mod flow as a recharge. Mod flow takes all of this, runs a 1 month simulation. This 1 month change that it has in terms of, pumping has happened, all that has happened, therefore irrigation water, that 1 month value is then spread over the entire next month for SWOT to use.
So that means after 30 days, whatever you get the water table levels, that will be the initial condition for the second month for SWOT.
Yeah, the SWOT is not affected by water table elevation. What SWOT is primarily receiving is how much water has been pumped out and is being supplied as irrigation. Because the wells and pumping is happening in mod flow. So all that is then applied over the, so about, let's say 25 mod flow grid cells are sitting on top of one SWOT subwatershed. So these 25 mod flow cells, basically you are, depending on where you have pumps, they're pumping water out. All that water is being supplied on top of SWOT as surface irrigation application. So that entire 1 month of water, for that 1 month time step is going to spread over 30 days for SWOT to use over the grid cells that are sitting on top of that, on top of that subwatershed. So there is a disparity in time scales.
So then, that is the case if water table elevations are not going into SWOT. So when you simulate for a long time, how only the mod flow is giving the change in water table elevation.
Yeah, SWOT cannot tell you anything about the water table. The thing is, the goal was to basically be able to have a good surface water model, because we have water application, a lot of irrigation. Farmers wanted, all of that to be represented, plus each and every well which mod flow has to have. So trying to combine them, it doesn't have to be SWOT, it doesn't have to be mod flow. You need good surface water model, or what you think is a good surface and a good groundwater model. You would have this challenge of trying to have them talk to each other. Actually, I made it sound simple. There are quite a few things that have to be exchanged properly. I just showed you the figure to indicate there are lots of processes that have to be managed when you do this. I didn't show you results, but you can see what the overall mass balance looks like and so on. Any other questions? Okay, so we have a few minutes. I'll also thank you all, because I believe this is my last talk in this workshop. It was very nice interacting with all of you. If you have any questions, I'm going to be still here at least to the end of the day today. So, well, we can have a short break. What's next? Yeah.